Okay, now I just need to select one obstacle, one valley. I can travel here, 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 here. I cannot travel around these angles. I can travel here, 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 here. I cannot travel here. I cannot travel here, 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 and it's continuous. So you see that this also is circular in nature, except for I haven't drawn it as circular in nature. So there are some angles where there are obstacles, there are some angles where there are no obstacles. You need to select the place where there are obstacles in these hills and valleys. So the valley that I'll select out of all the options which are available to me will be governed by an objective criterion. Now there are two objective criterions. Number one, I need to move closer or in the direction of goal. So that's my objective one. And here let us say the goal was actually at 60 degrees. So I say this is theta goal, where theta goal is equal to a tan 2 goal y minus qy and goal x minus qx. So I wanted to move over here, but then maybe I move here, maybe I move here. I want to be as close as possible to the goal, and remember it's circular. So if the goal would have been here, then this is free. So 360 and 0 are the same thing. So you can measure the distance in two ways. So either traveling in this direction or traveling in this direction. The moment you come here, you go here, and that's what I said, that use a tan 2. So the objective is given by theta minus theta goal, and of course I'll have to cast it into minus pi to pi range. So it's a tan 2 sine of this angle and cos of this angle, so that it becomes between minus pi and pi, and plus minus doesn't matter, so it's the absolute value of this. Now the other thing that I may want to do is I want to maximize clearance. I don't want to kiss obstacles. I want to be far away from obstacles, because vector field histogram, you want to be away from all obstacles. You want to maximize clearance. So my objective 2 is I need to maximize angular clearance. So what that means is that I want to be as far away from these valleys as possible, from these hills as possible. So this is okay, it's free, but then it's very close to obstacle. This is better, this is better, this is better. This is again bad because it's close to this one. This is bad because it's close to this one. I want to be as far away from the valleys as possible, from the hills as possible. Now, whenever you've got two objective measure and you need to optimize for them simultaneously, there are various philosophies. Take a weighted addition, do something else. So whenever you've got two objective measures, you eventually have multiple ways by which both the objective measures can be used simultaneously to get to one objective measure that is to be maximized, or you select a value which optimizes that objective measure. Here what we're going to do is something which is typical robotics. So I say there are two objective measures, and if there are two objective measures, all that I do is that I put a threshold on the objective measures so that I put the constraints on both the objective measures and see which ones of them are firing, and after that I see which one are firing, then I apply a primary objective measure and a secondary objective measure, and my secondary objective measure only gets into play when there is a tie break at my primary objective measure. So I say that I want to move closer in the direction to the goal. I say the same thing, a maximum deviation of alpha is allowed. Now, if I say a maximum deviation of alpha is allowed, this is the angle to goal, and say this is alpha. So I'll only consider these angular range. The second one, I say maximize angular range. I say subjected to a max of C max. Now I guess it that the one that I drew is too simple, so let's draw a little bit more complicated angular range. So lots of obstacles, lots of free regions. And some very free regions. Okay, so that is what is my, let me put another one. Polar obstacle density, so 0 or 1. So this is HI binarized, and this is the angle from 0 to 2 pi. And let me arbitrarily mark anything as the goal. So I say that is theta g, and I say this is alpha. So what I'll do is I will use this as my primary measure, and this will be a secondary measure. So objective 1 is secondary and objective 2 is primary. So select the widest valley. So now within this red mark, select the widest valley. And when I select the widest valley, I need to make sure that I have applied a constraint of Cmax over here. So I need to only select the widest valley till it is within 2 Cmax distance. Because after that it's wide enough. So I haven't shown Cmax over here. So this is too narrow. This is narrow. This is narrow. And I'm stuck with this thing and this thing over here. And if this is greater than 2C max and this is greater than 2C max, then I virtually have no choice between these two. So both of these are equally wide. Then I apply my primary criterion. This is closer to theta g as compared to this, so I'll select this one. So based on the primary criterion, there was a tiebreaker between these two because both these had a clearance more than 2C max, and because both of them had a clearance more than 2C max, I used the primary criterion, which is which one is closer to the goal. This one is closer to the goal. So I selected this one. Hypothetically, if both of them were less than 2C max, so then I would have said that this one gets selected because this is the widest. And because there's no tiebreaker, both of them have clearance less than 2C max, and this one is the widest, so this one would have been selected. Now, so that's the first problem. So that's my problem number one. I need to select a candidate. Why candidate? Select the best valley. So given a binarized histogram, my first problem is to select a valley, and that's what I've solved it. So again, to say there were two objective criterions, and because there were two objective criterions, I first apply a limit to both of them. I applied limit of alpha to angular deviation. I applied a limit of 2c max to the widest and valleys to be considered. Then I said angular clearance is my primary criterion. Out of all the var candidates which qualify my angular deviation of alpha, I'll select the widest one, and if there's a tiebreaker, then I'll apply the primary criterion. And my tiebreaker was whenever a valley has more than 2c max distance or angular clearance, then I say that my tiebreaker gets invoked. Now my problem number 2 is select an angle from the valley. So now what I need to do is I need to select an angle from the valley. So now let me just draw the possible cases, and I will only be drawing the selected valley. So I'll just draw the left and the right boundary of the valley. And let's say that theta goal is here. And let's say this is greater than equal to 2 times C max. So now what I'll do is from theta goal, I will go to C max, and this will be my theta selected. Because C max is the maximum clearance that I want. I could have gone more over here, but then what that would have done is it would have maximized my clearance, which is already at the maximum of C max, and my primary criterion would have suffered unnecessarily, even though my secondary criterion would have suffered even though my primary criterion is at the maximum value possible. So that's case number 1. I can have the opposite case as well if theta goal was here and this was my wide valley. So then I'll go C max here, and this would have been my theta selected. There are other cases as well. So this was the case with wide valleys. Let's take the cases of narrow valleys. In fact, let's take another case of wide valley. So that's a wide valley, and I say this is theta goal, and this is greater than equal to C max, this is greater than equal to C max. So this is also my theta selected. My primary criterion is maximized, it's at C max. My secondary criterion is maximized, it's optimized, it is at 0. Best primary, best secondary. Clearance more than C max already, and angular deviation 0 already. What else do you need in life? Goal is straight ahead of you. There is no obstacle nearby. Just walk to the goal. Let's take the narrow cases. So that's a narrow case. Now I'll have to go to the middle of this. Now I'll have to go to the middle of this. And if I say I'll have to go to exactly the middle of this, what I basically mean is let this be theta 1 and theta 2. So theta selected will be equal to theta 1 plus theta 2 by 2. And answer doesn't matter if theta goal was this, then also the same case would have occurred. I'll go by theta 1 plus theta 2 by 2 because my primary objective cannot be maximized more than theta 2 minus theta 1 by 2. That's a maximum clearance possible. I cannot maximize it up. So I'm going in a congested route, I'm going in narrow corridor, I'm going in a corridor where the deviation, where there are obstacles at smaller angular region than what I expect. But I will have to go in because that's the only option available. There are obstacles nearby. I'm going to a congested region, but I will have to go it. So I'll maximize my clearance as much as I can. So this clearance is the one that will be given by theta 2 minus theta 1 by 2. That's a maximum that I can get. And therefore, what really happens around in this algorithm is something very interesting. So what I do is I stand up and I look at the window of W cross W. I construct polar obstacle density. I do all kinds of losing of information, histogramming, binarization. And after binarization, I just have two objective criterion. I want to be as close as possible to the goal, and I want to maximize my clearance. Both have thresholds, and the second one is primary, the first one is secondary. I select that angle, I move, and after that I apply the algorithm again. I absolutely apply the algorithm again. And once I apply the algorithm again, that's exactly what happens. So let's take it up in a slightly more visual sense. So this is my obstacle, that's my angles, that's the obstacle, it has certain certainty. So if I apply the polar histogram density in angles of 20 degrees, here it's from minus pi to pi. So that's a one. So you can see that around 0 it has a peak because this is close and there are too many obstacles within this 0 to 20 degree range. And similarly here, around 120 to 140, this is maximum because there are too many obstacles around over here, and similarly around over here. So around 120 to minus 120 to minus 160, there are too many obstacles around over here because this is here. So you clearly see these obstacles. And what I do is then I smoothen it up like this. So you see the nice smooth curve, and then you apply this threshold, and then you do this thing. And then I say, okay, which valley do I select? That's my angle to goal. So there are 1, 2, 3 valleys. So this one is far from goal. So valley 1 is too far. So it doesn't qualify this thing. So it's either this or this. Now the one which is widest is this. So I select this. And then I just need to go Cmax away. So from angle to go, I go Cmax away. So this is the one that I finally select. So I'll go at approximately 60 degrees, and approximately 60 degrees is this angle, and it appears to be correct. So there is reasonable distance from the obstacle, and of course at the same time I can only decide in multiples of 20 because of this binarization, and at the same time you see that there is absolutely no obstacle. In fact, at 60 degrees there was never an obstacle, let go being far away, and the certain uncertainties have been taken care of. So that's how I decide based on the vector field histogram algorithm. Now again, I did not incorporate the size of the obstacle. So if you have W cross W, W cross W, so instead of x0, y0, reduce this to a point mass, and every x0, y0 gets inflated by the radius of the robot, and all these are obstacles as well. So you just apply exactly the same fundamental, and you know this is x0, y0, this is the radius of the robot, which is say rho r. So you can measure both these angles. So you know the angular range gamma O. and the same formulas will hold good. So that's a perpendicular. And because that's a perpendicular, you know the hypotenuse d of q comma x0 y0. So it's the same hypotenuse upon rho r. And this point obstacle will be valid within this range. So that's the first thing that you can obviously do. And if you do that, it's called as the vector field histogram plus algorithm. So it adds the radius of the robot. Now again, there's a problem over here, the same problem that we discussed with the velocity obstacles. And when we are dealing with velocity obstacle, we said that you can keep on switching the side, and we had a hybrid reciprocal velocity obstacle. So I won't repeat the same thing again. The same thing is possible in the corridors over here. So sometimes you select this corridor, 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 and you keep on switching here and there, just like our robot was doing there, in exactly the same scenario. So, and that's bad. Same as velocity obstacle, that was extremely bad. Here also that is extremely bad, and I have to avoid it at any cost. So we apply exactly the same thing. So we apply it at the binarization level. So we keep two thresholds, and the thresholds are set so if something is extremely high, it's an obstacle. If something is extremely low, it's not an obstacle. If something is intermediate, you look at previously was it an obstacle or not. If previously it wasn't an obstacle, then you don't consider it up, so that the same candidate value gets selected multiple times. So instead of having a strict, and that's exactly what we said previously. So previously it was, I avoid you on the left hand side, so I keep on avoiding in the left, unless you prove it that right is significantly better. If I select this value, I do binarization such that the same value comes, so these are never obstacles. If I'm doubtful, these are not obstacles. And I try to select this value again and again so that I don't keep on oscillating. That's again something that is done in the vector field histogram algorithm. Now, in the vector field histogram plus algorithm, now one thing which we haven't discussed is we started our discussion with the narrow corridor like this, and what unfortunately can happen is that when you convert this into binarization, all you get is, okay, that's binarized. I need to plot it as histogram. And that is your normal threshold of alpha. Oops, no path possible. What do you do? So if no value can get selected as per the objective measure, as per the constraints, then you need to loosen up the constraints. That's what we people do. You can only take this course if you have more than 9 CGPA, if you have excellent track record, if you have a lot of practical exposure to whatever machine learning, AI, if you got AA plus in machine learning, AI, if you look extremely bright, blah, 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 nobody joins the course, and then we're like, okay, your past records don't matter, grades don't matter, your intellect level doesn't matter, sometimes your year of study doesn't matter. So we let go all the constraints so that we at least get some students. The same thing is over here. So there were two important thresholds that we applied previously, and those are important. That's the first threshold. So if you don't get enough good candidate values, you need to loosen it up. And the threshold, the rule of thumb is, if you want to enter narrow corridors, then you need to have this factor such that most of the regions are obstacle free, which means that this factor would have to be sufficiently and appropriately increased to a limit such that most of the times this condition holds good and this condition rarely happens. So you're saying mostly it's free. So whenever you travel close to the obstacle, that's what happens. When unfortunately you might have to go near to the obstacles, narrow corridors and these regions. And when you go extremely close to the corridors, you say that, okay, let me mess up with this parameter, let me increase this parameter so that it doesn't get bogged off that, okay, there are so many obstacles all around me. It's congested region. So you increase this factor and mostly you say that things are obstacle free. And the other important factor that we also considered was this factor. So it was a Cmax. Now sometimes you need to reduce it up so that, I mean, what does this factor do? It says that going far away is better than going in this narrow corridor. You want your robot to enter a narrow corridor, so you'll have to reduce this factor appropriately, take risk. And that's a problem of entering narrow corridor. You have to take a risk, you have to enter, you have to set these factors low, and you get it when you get trapped. There are all obstacles around, there is zero candidate values that qualify. So you redo the algorithm, you reduce the parameters, and that's called as adaptively setting the parameter. So you look at the obstacle plot densities, you look at the candidate values generated, and you say that, hey, these parameters are too high, let me reduce it up appropriately. And then you see that the robot, which was earlier, no, I'll not enter the narrow corridors, is suddenly more ambitious, it's more risk-taking, it is going more towards entering up of the corridors that you would have otherwise avoided at any cost. And that's the importance of the parameter. That also goes to prove that once you need to change your agent behavior so that it enters into such difficult regions, the aggressive behavior, the behavior that I will go inside it, I'll try to circumvent myself in dense regions, then you need to appropriately modify the parameters. And that's again an algorithm which can let the agent go towards the obstacle, away from the obstacle, depending upon how do you set Cmax and how do you set in the binarization threshold into your algorithmic framework.